Assalamu alaikum and thank you for being here. I am Abubakar Salihu Abba and today I will present our collaborative research titled Enhanced Minority Class for Oil Spill Detection by integrating weighted data class into Max Arsenal architecture known as WMax Arsenal. Actually, this collaborative research addresses a critical research gap in oil spill detection, and I'm excited to share our findings with you. Oil spill actually is nothing but the release of petroleum hydrocarbons such as crude oil or refined oil into the marine environment, either accidental or deliberate, due to the human activities or natural disaster. So when this oil spill occur, it actually pollutes our environment, especially the offshore environment, the marine environment. Look at this image, it actually polluted the environment, thereby causing a negative effect to the maritime and economic at large. So what actually motivates us to conduct this study is the negative effect of oil spills to the economic growth and to environment, thereby necessitating the rapid and accurate detection model. Secondly, most of the existing deep learning models, especially the families of Max Arsenal model, struggle with class imbalance, especially the foreground background class imbalance. What I mean by foreground background class imbalance is the type of imbalance whereby on a single image you have all your classes. So among all your classes, the class of your concern will have a limited number of pixels. So solving this kind of imbalance is beyond a data argumentation. So that is why most of the deep learning model suffer in solving this class imbalance. These are some of the related works that have been conducted in the field of oil spill detection. But most of the existing work ignore class imbalance when conducting their research, or they use a suboptimal approach like data argumentation. And as I said earlier, applying data argumentation to solve a foreground background class imbalance is not possible actually. It may not yield to an optimal solution. That is why most of the existing models fail to address the class imbalance. So our research gap here focuses on the issue whereby the majority of the model perform better on the majority class, but underperform on the minority class. And there is a limited works on integrating multi-data class method, whereby in enhancing the minority class precision. That is why we feel it is important to bridge this gap. So in trying to bridge this gap, we propose an enhanced Max Arsenal known as weighted Max Arsenal model, thereby integrating what we call a data class mechanism that will improve the detection of minority class based on this formula. So we assign a weight to our class of interest, that is the minority class, whereby the, the weight will start from 1 and it will keep increasing during the training until when we get the optimal result so that the model can learn very well on the class of interest, that's the minority class, without affecting the majority class. This is our proposed model architecture. If you look at this architecture, this is an enhanced version or modified version of Max Arsenal, whereby we integrated things, a lot of things on it. For example, we have added a what we call an oil spill attention mechanism known as convolutional block attention. And we have added a what we call a weighted cross entropy loss. Here, we we have added a what we call a convolutional LSTM, and we have added what we call an squeeze and excited block. Here we have added a weighted cross entropy loss. All these modifications like integration we have done in order to improve the efficiency of the deep learning model in terms of handling class imbalance, especially foreground background class imbalance, whereby in a single image we have five classes, and among these five classes, the class of our interest have a limited number of pixels compared to the other class. So by doing so, it is expected that now the model can learn more and more of this type of imbalanced class. This is a description of our data set. This table shows the number of classes that we have in our dataset. We have five classes. Number one, we have the sea background with a black color. Number two, we have the oil spill with a cyan color. And number three, we have lookalike with a red color. And number four, we have sheep with a white brown color. And the fifth one, we have a green, a land with area with a green color. Looking at the image here, this is the star image and this is the ground truth. If you look at this cyan color represents an oil spill, while this red represents a look-alike, and this green represents a land area, and this black represents a sea background, and we have a one small brown here represent a ship. So if you look at this image, in most of our images from our data set, the class of our interest, that is the oil space class, this same color, has a limited number of pixels compared to the either a land area or the sea background. So as such, it appears very small number of pixels. So there is an imbalance between the other classes. That is why detecting that class is very difficult in most of the model. And that's why we are proposing an improved version of Max Arsenal known as a weighted Max Arsenal to handle such kind of problem. The data pre-processing is necessary for us to process our data so that we can fit to our developed model. First of all, we have reduced the size of our image to 256 by 256 for computational efficiency and consistency. And we have applied a lot of augmentation such as random horizontal clipping, random rotation, color jittering, brightness adjustment, and contrast adjustment. All these things so that the model can learn different formats of the image. So again, we have set a suitable parameters for our developed model in order to perform better. So right from the number of epoch up to the momentum, all these things are parameters that will help to develop a robustness model that will handle our class imbalance. These are the qualitative result comparison with existing model. So in comparison with a model, our model perform actually better in terms of intersection over union, where we have 81% compared to the young Metal 2024, where we have a 78%, while we have a 81%. In terms of accuracy, we have the PCL F1 score, we have 96% F1 score compared to the Delamy et al. 23, we have a 94% F1 score. And in terms of recall, we have a 96% recall compared to the 94% recall of the same Delamy et al. And we have 93% of precision compared to 94% of precision of the same Pelini 2012. And in terms of accuracy, we are almost the same in terms of accuracy. This shows how our proposed model is performing better in comparison with the existing deep learning models. So this is how our loss is been decreasing both during training and validation. This is to show that the model is learning very, very well. These are the sample of the qualitative results. All these column shows the number of input image that we have input based on data set. This is indicate the number of what we call the ground truth that show the actual oil spill in the image. And this is what our model is being predicted. By doing so, it actually show that the model, our proposed model, is performing better in terms of the prediction, despite the oil spill class has a what very limited number of pixels. But because of the introduction that we have made that will solve the class imbalance, the model can be able to predict it very well. So in conclusion, actually this research proposed a robust improvement to a traditional deep learning architecture for oil spill detection by introducing the what we call a weighted Max Arsenal model. So here, the key contribution are what? In terms of architecture, one, we have successfully integrated a weighted data class mechanism or approach into the existing Max Arsenal for addressing class imbalance in oil spill. And by doing so, we have actually achieved a 1% accurate percent improvement in terms of intersection over union, which is very critical performance evaluation metrics in segmentation. And we have actually enhanced multi-class sensitivity whereby the dynamic weighting it reduced the false negative of the what for the parcel pixel so that we have a few number of false negative in our result. So actually there is no solution that is perfect. However, our own model have some drawback or limitation. One is our model actually depend on a high quality of synthetic aperture radar image known as SAR image for the training of our model. And we have a high computational overhead from the weighted optimization because of the adding this weight. But in the future, it is expected that we are going to extend to a multimodal data whereby we can combine the optical and the sat image for the robustness and we can explore the real-time development on a drone or satellite device. So thank you for listening to my presentation. Terry Makase.